So let's talk about the problem before the embeddings. So before the uh, embeddings, natural language processing use token IDs, one-hot vector. Examples is word cat. Its token ID is 4937. The dog is has a value of token ID of 3899. The issue is these numbers are only labels. The model cannot understand that cat and dog are related. Both are animals, both are pets, both are closer in meaning than banana. So cat tokens ID is 4937, dog is 3899, banana is 721. These IDs contain zero semantic meaning. So what embeddings actually are? An embedding transforms word into a dense numerical vector. Instead of cat is equivalent to the label of 4937 token IDs, we get the cat is equivalent to the vector value that contains of numerical values like 0.24, negative 0.81, 0.55, 0.91, and so on and so forth. This vector exists in a high dimensional semantic space. So the core goal of embeddings is the main objective is the similar meanings is close vectors. Different meanings is distant vectors. So the word pair, like for example cat and dog, the distance is close. The king and queen, the distance is close. The apple and banana, the distance is close. The cat and airplane, its distance is far. This is the revolutionary idea. The model no longer memorizes words or isolated symbols. It learns relationships, context, categories, semantic similarity. The map of meaning. The map of meaning. So the map of meaning is imagine words position in space, like for example the animal contains animal region as near close together, dog, cat, rabbit, and banana, apple, orange, like form a cluster or regions like that. This is why embeddings are powerful. So what's one hot vectors versus embeddings? So one hot representation, suppose vocabulary size equivalent to 5. So the cat is equivalent to 10000. The dog is 01000. Banana is 00100. The problem is every word is equivalently distant. The system cannot learn. Cat is closer to dog. Banana is a fruit. King relates to queen. The transcript explains this sa, um, limitations. So there's a lot of limitations there. So let's embedding solve this instead we use the cat is equivalent to 0.2, zero point 0.7 and negative 0.1. The dog is 0.19, 0.68 and negative 0.08. These vectors are numerically similar. That similarity mathematically represents semantic similarity. So dimension represent abstract concept. Like for example, the gender, royalty, and age. For example, the word man and its the gender is male, the royalty is no, the age is adult. For example, woman and its gender female, the royalty is no, the age is adult. The word king and the gender male, the royalty is yes, the age is adult. So the word is prince, the gender is male, the royalty is yes, the age is young. So in reality, modern embeddings use 100 dimensions, 300 dimensions, 768 dimensions, and even 4096 plus dimensions. And concepts are spread across many dimensions. Not dimension 1 is equal to gender, dimension 2 is royalty. Instead, semantic meaning is distributed geometrically across many dimensions working together. This is exactly uh, the meaning of it. So embeddings learns automatically. One of the most important concepts is humans do not manually define meaning. The model learns meaning automatically from data. The transcript explains words appearing in similar contexts develop similar embeddings. This is called distributional hypothesis. Words use similar contexts tend to have similar meanings. Example, the cat drinks milk, the dog drinks milk. So the model notices the cat and dog appear in similar sentence positions. There are similar words inside similar contexts. So their vectors slowly move closer during training. So how training actually changes embeddings? Initially vectors are random, like cat is like for example its value is 0.11, negative 0.42, 0.88, and the dog is negative 0.093. 0.15.01. During training, propagation plus optimize and gradually adjust them. So loss function measures prediction error, gradients calculates adjustment direction, optimize their updates parameters. Embeddings themselves are trainable parameters. So um, yes, embedding vectors are learned weights. So the king minus 1 plus 1 is equal to queen analogy. This is one of the most famous embedding demonstration. So mathematically, king minus 1 plus 1 is equal to queen. So conceptually, king is equivalent to male royalty. So subtract man, removes male concept, and add woman royalty. So woman plus royalty is queen. And female concept versus queen. This show embeddings in code semantic relationship geometrically. So cosine similarity. The transcript or the yeah um, um, in that in the learning materials that I have read explains cosine similarity in detail. So cosine similarity measures angle between vectors, not raw distance. So the formula is cosine like a times b divided by the absolute value of a times absolute value of b. So in interpretation, the cosine similarity, um, if its value is 1, the meaning identical direction. If its value is 0, it's unrelated. If it's negative 1, it's opposite. So king, queen, high similarity. Apple and orange, high similarity. King and screwdriver is low similarity. So embedding layer in neural networks. For example, we have the n-ended embedding. Its parameter is vocabulary size and the embedding dim. Like suppose we have the vocabulary size is 10,000 and its embedding dimension is 300. This means 10,000 words. Each word has 300 dimensional vector. So internally, embedding matrix the shape is 10,000 and its embedding and its dimension is 300. It show is equivalent to one word vector. So how it works. So if token ID is 4,907 and then we put in embedding matrix and the embedding vector, that vector becomes a neural network input and this connects directly uh, like we fed it in a linear layer. So the embedding vector becomes numerical and semantic representative fed into the network. And static embeddings, older systems, word to vec, rove, fast text, uh, this generate one fixed vector per word. The problem, like for example, if what the word bat always has the same vector, but bat can mean flying animal, baseball bat. Static embeddings cannot separate meanings. So here comes the contextual embeddings. Modern models solve this. So the BERT, the GPT, Elmo, the transcript explains this transition. So from flying bat to baseball bat produce different vectors because surrounding words influence the embedding. This is huge. Meaning is now context dependent. Now, how BERT creates contextual embeddings? BERT processes the entire sentence. So the bat flew at night creates one vector for bat, but the sentence he swung the bat creates another. This is why contextual embeddings are far more powerful. So why transform and change NLP? Transformers allow contention mechanisms, contextual understanding, dynamic embeddings, long-range relationships. So embeddings are no longer isolated, they evolve depending on neighboring words, sentence structures, context, syntax, semantics. Why embeddings are so powerful? So embedding allow neural networks to generalize, understand similarity, cluster concepts, transfer knowledge, understand analogies, perform semantic search, power chatbots, power LLMs without embeddings. Modern NLP would barely work. So the full pipeline here is the natural language processing embedding pipeline is from raw text to tokenization, the token IDs, the embedding layer, the then semantic vector, neural network, predictions. So the entire concept is a foundation of BERT, GPT, LLMS, semantic search, recommendation systems, vector databases. So So language meaning becomes geometry. Words become positions, multi-dimensional space. So meaning becomes distance, direction, cluster, angles, vector, arithmetic. That's your revolutionary embeddings introduced. So that's it.